Hello. In this presentation we'll be going over the model-based zoo. So basically a bunch of papers and blog posts that I've looked at that show some different model-based applications in reinforcement learning, which we can use for inspiration or just to know like how we might apply model-based methods. This presentation doesn't delve that much into the math or the implementation details. All right, so let's start with AlphaGo 0, which we probably all heard about in the news, was very successful. So this uses Monte Carlo tree search, and the Monte Carlo tree search bootstraps off a value function. The value function is the probability of winning the game. So the value function, it is trained using the actual game result. So you don't do any training until the game is over and you know whether you actually won or lost, right? So there's no bootstrapping when we train the value function, which means that there's no bias in training the value function, right? There might be bias in the Monte Carlo tree search because it's using the value function. So until the value function is perfect, there's going to be some bias from the value function to the Monte Carlo tree search. But the training, there's some initial value function and bias due to our limitations of our neural network model, but the training is introducing no additional bias to the value function. Now the Monte Carlo tree search results, they actually train a policy. So they're using something like Dagger, but softened. So in Dagger, you say, this was the right answer. You should predict this. So they modify this slightly. So they're like, okay, these ones, this was the best answer, but these ones also gave pretty good results. So, have a relatively high return for all of those results, and all the other ones you should have a very low probability of. So using these softened training targets gives a better training signal if you know how to do it right. So now this policy, in turn, is used to narrow the sequence of actions that Monte Carlo tree search evaluates. So this is really important. In Go, you've got like 19 times 19. You have almost 400 possible moves at each step. So it's important that we learn to narrow this down so that our Monte Carlo tree search can be much more targeted, right? So that we can go to more depth because we automatically eliminate a whole bunch of actions without even taking them once. So I'd say that's why they have a policy as well as a value function, right? The value function, we'd actually have to execute the action, then run the whole board through a neural network to figure out whether it was a good move or not. Whereas with our policy, it can evaluate all the possible actions at once from one board configuration. Cool. Okay. So the policy helps narrow down the Monte Carlo tree search. The Monte Carlo tree search in turn is training the policy to tell it which things it's likely to find were good, right? And so how does the policy narrow down things for the Monte Carlo tree search? Well, we have this optimism bias in Monte Carlo tree search. And so we have the Q estimate so far from our search, and then we have the optimism bias, and we can see this optimum bias here incorporates the probability from our policy in here. So if this probability is small, we'll probably never investigate that node, right? They add a bit of randomness, so eventually we'll kind of always investigate each node, but on most turns we wouldn't investigate many nodes. Cool, so that's AlphaGo 0. All right, let's move on. So we'll be covering neural networks dynamics model. This is a global model, and then using that to kind of kickstart model-free policy learning. Cool. So this paper uses a medium-sized neural network to train a global model. Global model. So it initially trains its model on just random action data. Amazing sample efficiency, uses model predictive control. It can follow arbitrary trajectories as long as you specify where the rewards are. And like I said, it makes training a model-free learner way quicker by kickstarting it to copy the model-based actions. So there's a great video here. So let me see. All right, let's watch a bit of the video here.
Here, the swimmer
so you have to specify these rewards here,
sparse desired center of mass
and then it can do it.
Guidance.
Let's skip forward.
Here, the same dynamics model of the swimmer is employed to perform a right turn.
Yeah.
The ant performs a sharp left turn. Next, we show results of the model-based approach on the task of moving straight forward. In order to achieve success on the task of moving forward, our model-based approach uses only 12,000 points, as opposed to the leading model-free approaches that use 4 million to 11 million points. This approach does, however, have shortcomings. While this approach is extremely sample efficient, it cannot always achieve the high desired rewards. Here, our model-based approach uses less data but achieves a slow forward gait, as opposed to model-free approaches that achieve running gaits. To achieve higher rewards while maintaining sample efficiency, we use the model-based approach as a burn-in for faster model-free learning. We first run our model-based approach to achieve steady forward-moving gaits. We then train a policy to imitate that behavior. Finally, we run a model-free algorithm on the pre-trained policy in order to achieve the desired high performance.
So it's a log scale here, so it trains quite a bit quicker. All right, let's go back. I'll probably play the next video. All right, so this approach assumes that we have access to the underlying reward function, so we can plan. We can create that reward function to have it execute arbitrary trajectories, or we just need to know what it is. So this only looks h time steps into the future with no bootstrapping here, and h is I think about 10. All right, so it's looking at a very short time horizon into the future, which allows it to, the model still works fairly well over those short time horizons, but it can't plan that well. Cool. So this is a bit about how they train it. Let's see if I can. Yeah, there we go. That's a bit about how they train it. I'm not going to go over this in detail. So how they do the model-based control. So they generate like 10,000 or something. They generate a bunch of random action sequences. Each sequence has 10 actions, and each action might have, be 17-dimensional or something. So a relatively short time horizon. So based on that, they can predict the future states and the future rewards, since we know the reward distribution, and then they can just pick the best one, right? So let's have a look at the algorithm. I won't go into details. That's the algorithm. So some examples. We already looked at some. We're also going to look here. So all right. So here, this is with a real robot trained in just 17 minutes here of real-world experience, and it can follow arbitrary trajectories. So again, showing the sample efficiency of model-free approaches. This is, I think, a fairly simple robot. But yeah, it's quite doable with a real robot. And oh yeah, then you can see these executing arbitrary paths as well. We'll look at more of these later. Oh, no, I'm done those. All right. Hold on. Yeah, no, we got more. Cool. So when we want to combine model-based control with reinforcement learning, then we need the reward distribution up front. So we initially train on the random data. Then we can collect some on-policy data where we try and get the maximum reward. And then we can train with that on-policy data and repeat that a few iterations, and we get much better results that way. And here's where we kickstart our model-free reinforcement learning algorithm using the model-based one. So yeah, I think they just use Dagger to initialize the model-free policy, and then I think they used TRPO, and it used apparently something like 1/3 of the training time that way with that kickstart. You can see it. The model-based approach did well, and then when it transferred to the model-free approach, it had some adjustment it needed to do, but then it overall is performing much quicker on this log scale than a purely model-free approach. Cool. And let's look at some results. So you need enough data to learn your dynamics model. On-policy data also helps you do better. So it seemed like a short time horizon of about 10 worked best, and we can kind of see why here. You see over very short time horizons here, the model is performing quite well, but then you start to see deviations, particularly in terms of x, the distance traveled, which is probably why the longer time horizons were not so helpful. They just added a bunch of overfitting to errors in the model. Cool. And so I found this claim interesting, that for many applications, the competence on a number of tasks is what we really need, rather than expert performance on a single task. And I think this makes sense. You want your robot to be able to fold your laundry and do your dishes and clean your windows and all that stuff. And if it takes 3 hours to fold your laundry, well, that's probably okay, especially if it can work day and night, you know? So yeah, so I found this quite interesting. Yep, and I think this is not the whole picture. But yeah, something to keep in mind. Cool. So let's move on to a more recent paper, which has some, additional ideas that improve upon that previous paper. So this uses an ensemble of models. So this is kind of, double Q learning, right? One model picks the best action, the other model evaluates it, because they have different errors, right? And so then you mostly solve the problem of overfitting to the errors in your Q function with double Q learning. Well, this is with an ensemble of models, we can help to solve the problem of overfitting to the errors in our models, right? So it's kind of the analogous next step for models. So also, one of the things, so they significantly reduce sample complexity, not surprising. Let's have a look at the algorithm. So here they're creating fictitious samples just by simulating using their model, and they're using that to train their TRPO, and they do that for a while, and then I think they have to collect some more real-world data to improve their models as well, and then they can do this, fictitious dreaming training of TRPO. So this is a more tightly connected training of your model-free algorithm with your model-based approach as well. So I thought this had some interesting ideas. I haven't read this paper in detail. If we want to do model-based stuff, I think it would be good to read this paper in more detail. So also, let me see. Here, Peter Ebel is a well-known name, so that kind of gives me some trust that this is a worthwhile paper. These other people might be, but I personally don't recognize the names. All right, let's move on to another interesting idea: curiosity-driven exploration. So Basically, this trains an inverse dynamics model to create latent features that only relate to the actions taken. Of course, this can be an iffy proposition. For their specific application, it seems like it was a great application of this for their specific game. Then it trains a forward model, and it gives a curiosity reward proportional to the error in the forward model. And this forward model is using the latent space trained by the inverse model. Yeah, so where it doesn't understand the forward model very well, maybe it should do some more exploration, right? Because that's, new territory for it. So that's basically how they implement curiosity. Let's look at this in more detail. So there we go. So this is their intrinsic curiosity model, or ICM. So first of all, they use okay, so you got your states, your policy gives you an action, and then your environment gives you the next state based on that action. So that's what's happening here. And so then we take all this data, we put it into our intrinsic curiosity model, which is what we have over here. So each state is used to produce features, and then based on those features, we try and predict, well, between these two states, what action was taken, right? So that's our inverse model. And so our inverse model helps to train these features. And then we use these features with the action to try and predict the next set of latent features. So the forward model is working in this latent space trained on the inverse model. And then there's going to be some error between this and our actual one, and this just becomes a reward that we feed in to our model-free learner, so it learns to take those actions to explore those states more until, over time, of course, it will learn the inverse model and the forward model well on those new states now that it's explored it, and then this curiosity reward will go away. Cool. And so it, of course, worked well on their chosen tasks. So they also did pixel-based curiosity. But for pixel-based curiosity, you could be curious about the shimmering of the leaves in the wind, because that keeps changing and you aren't able to predict that well. So for certain tasks, pixel-based will not work that well, whereas using the latent space may work well for certain tasks. So let's look at that here. So when you have fairly dense rewards, everything works. When you have very sparse rewards, this curiosity signal really, it's the only thing that works, because otherwise, yeah, it doesn't have enough of a signal to actually explore enough to actually find where the rewards are, right? So yeah, for certain applications, this can make a huge difference. And I think there's certain applications where it won't work, but maybe we can modify it to make it work better. We might use variational auto-encoders instead of, or as well as, the inverse model to train the feature space, I think. Cool. So that was a neat idea, I think. Now, next we're going to move on to temporal difference models. Oh yeah, so that stands for temporal difference models. So these are a very different kind of model. They're quite cool with applications in certain areas, but maybe that can be expanded over time to apply in more areas. So they give the example. When we learn to ride a bike, we use basically a model-free approach, right? We don't calculate the physics and whatnot and figure out how much torque we should apply at each of our joints to make the biking work. No, we just use trial and error and we learn to bike. Now, once we want to actually get somewhere, I don't know why he's hitchhiking, now we use a model-based approach. Okay, we need to bike there, and then bike there, and then bike there, and I'll arrive at the destination that I want to get to, the beach or whatever, right? So at a small time scale, we use model-free stuff, and that's, remember, how you get the most performance. At a larger time scale, we use planning, which, at a larger time scale, that's where we need our sample efficiency, right? So yeah, that's how we humans tend to work, and we're at longer time scales, we're kind of planning in a kind of more abstract way as well. Now, Of course, there's actually interplay between the two, but yeah, this is the basic idea. Cool. Now, what do we actually do with model-based methods now? Well, we plan in increments of our time step, which is basically 1/100th of a second. So we are actually planning, okay, I'm going to apply this torque at this joint here. I'm going to apply this much torque at this time step, and the next time I'll apply this much torque on this joint. And yeah, so we do these very tiny time steps, and we try and plan how to get somewhere with that. Yeah, and it works, but only over very short time steps because of errors in our model over longer time steps, unless we have a perfect dynamics model. So temporal difference models flip this on their head, allowing planning more like what humans do. So they create these goal-conditioned Q functions, and so this Q function is like how close can you get to a certain goal state in time tau. So maybe you start here, and in time tau you could get here, and if your goal is here, well, that's the distance to your goal state. So that's what this Q function would give you for that time tau, and this goal state and this initial state. Cool. Okay, so that's our goal conditioned Q function. Now, how would we update this Q function? Well, this is what makes sense to me. I won't go over the details. So now once we have this goal conditioned Q function, then we can break our task into larger time steps of k of the original time steps. So maybe k is 10 seconds or a minute. So we plan it in minute increments now. So basically all these tiny time steps, we can instead just do fewer, bigger time steps to try and plan how to get there. Cool. So we see, okay, I can't get here in 1 minute, but I can get here in 1 minute, and I could also get here or here. You know, I could get to these points in 1 minute, and then in 1 more minute, well, from these points I can get to these points, and then in 1 more minute from those points I can get to kind of those points. So you kind of get a frontier, and then after a certain number of minutes you figure out, oh yeah, I can actually get to my goal. All right, so what are some downsides of this approach? Well, we can only optimize the reward at the states that we actually see, which is now only every kth step. This only works with deterministic transitions so far, although there may be ways to extend that. And well, here they're showing we just have 2 dimensions, right? But the cursive dimensionality, like with any model-based method, it will get you as you go to higher dimensional spaces with more steps of planning, right? Cool. So in experiments, this works very well. Low sample complexity. So on this task, you can see TDM here. It's right at the bottom, and this purple line is another model-based method. So yeah, great sample complexity still, because it does have, now for the short time scales, we're basically doing something model-free, like Q-learning, right? But for the longer time scales, we're doing something model-based still. So this also seems to produce quite high performance. So you can see here, TDM is giving you the best performance as well. So I suspect that our model-free algorithms with right fine-tuning would eventually get to the same performance as TDM. But TDM is getting there quickly, like a model-based method. Excellent sample efficiency. But since over the short time scales it's using model-free methods, it's actually has excellent performance as well. So it's getting both of those things at once in a single algorithm, which is pretty cool. Yep, but it has the limitations that I discussed earlier. So I don't know, this seems like this is an exciting area for future research, but it's kind of not ready again for prime time in a lot of applications. In certain applications it is. All right. So lastly, I want to discuss one tool that I think it's good for us to keep in our tool belt. This isn't just for model-based learning, but it would be useful for model-based learning for kind of compressing our search space. So let's have a look at this. So variational autoencoders, you take some original digits and then you pass it through and you create a latent space, and then you expand that latent space back to try and reproduce the original inputs, in this case images. And so you can see these images are basically the same as these, except they're a bit fuzzier, because when you compress something and then you expand it, well, in this case it's a lossy compression, so you aren't able to totally recover what you had before. So the neural network architecture of variational autoencoders looks like this. You've got your encoder, and then you have your mean vector. You also have a standard deviation vector, and then you sample from those, and then you take this, and then you try and decode that and get back the cat. And so you're adding some noise in here. You're also training this with a loss here, where this loss is trying to make we have this KL divergence term, which is trying to make all these standard deviations 1 with mean 0, right? And so we want to minimize this reconstruction loss, but we're also trying to, make these unit normals. So it's kind of trying to trade off both of those, the inconsistent goals. So how does this compare to a standard autoencoder? So it has an incentive not to use units that it doesn't need. If it doesn't really need a unit, can you just say, okay, I'll give it mean 0, standard deviation 1, and I'll make this KL divergence 0, right? I can minimize that. If it needs the unit to minimize the reconstruction loss, well then, okay, it'll incur some cost here. So it'll do the most efficient encoding possible. So this kind of more softly encourages better generalization by having a smaller latent space, rather than a harder version where we strictly reduce the number of nodes available to the neural network. So also, each latent variable will probably only encode a single bit of the spectrum, because we don't want to pass too much information through each node here, because we want to add a fair bit of noise to minimize this term. So kind of each node can only encode kind of one kind of variation, if this is strong enough. Cool. So how can we use these as generative models? Well, so I'm not totally clear on this, but basically it would be wasteful, given this KL divergence, to kind of not use the entire state space, or not use the entire latent space. And so if all of it's used, then everything in the latent space is basically corresponds to something real that is near to something that's actually being observed. So then we can just sample from it with normal 0, 1, and when we decode it, we should get something fairly reasonable, which is pretty cool. So we can imagine states that we might want to try and get to this way in reinforcement learning. So yeah, that's cool. So yeah, in reinforcement learning, I see this being useful for reducing the dimensionality of our state space to search over, working better than just standard autoencoders. And since we can generate new states well, this could be a way for us to, train our TDM model. Generate a state, let's try and get to that state, generate another state, try and get to that state. Yeah, and then we could do a search over, okay, in this latent space, what points can I get to within k steps using TDM? So yeah, it seems to have potential. Cool. And that is it. Thank you again for watching.